formula for probability? What is the formula? Or no, yeah, what's the definition and/or formula for probability? It is
something in exploratorial okay, no.
Factorial?
Like, very good. That's what it's called.
But that's not for probability. Probability is just a fraction.
Oh, just
What's? I think you're thinking about permutations and combinations.
Oh, okay, that's it.
Now, what's just the probability? What is it? What's what?
All possible.
Yeah, exactly. 1 over total, which is the event you want, and the total, which is your sample space. Yeah, there we go. All right, so that's probability. And when do you multiply probabilities? What's the key word that tells you to multiply probabilities? Yeah, and. I think I heard somebody say and. You see the word and, that's when you multiply. And when do you add probabilities? When you see the word or. Okay, very good. And then what is a factorial? Man, I think that's what Simone was talking about. Factorial is when you multiply, you start with a given number, so like 5 factorial, and then you multiply 5 times 4 times 3 times 2 times 1. So that's a factorial. And that is a natural expression of a sample space that is getting smaller and smaller and smaller. So for instance, if you wanted to just take 5 of you and put them in order in terms of the fastest running times, then the first place person, there's 5 choices for first place. And then once you give that person first place, now there's only 4 people left to assign second place. And after you give that person second place, there's only 3 people left to take third place, and so on. So these numbers are really representations of the sample space. That's how many people are left to choose from. So here you have 5 people to choose from, now only 4 people to choose from, now only 3 people to choose from, etc. All right, that's a factorial. What is a permutation? So a permutation, we had a particular formula, permutation, and that was NPR, which was n factorial, and Michelle, this is what you were saying, n minus r factorial?
Yeah.
What are we doing here? What does n represent and what does r represent? We say out of n objects, then what? Yeah, permute r of them. And that means put r of them in order. Permute r of them. Okay, so that's a permutation, and the key thing there is that order. A permutation has order. Okay, and then what is a combination?
Group?
Yeah, group them. Very good. That's a perfect word for it. So that's n factorial over n minus r factorial, and that means out of n objects, group r of them. And putting them in a group does not put them in order. It just puts them in a group. So in a combination, there is no order. Okay, so those are all the major ideas that we talked about last time. And today we will just wrap up what we were doing in chapter 8, and then we'll move on to chapter 9. So everyone look at our calendar. This is definitely not our last day together. We still have 3 more days after this, but this is our last class period. So today we wrap up chapter 9, and then on Thursday you all get to take a test. And then the next week on Tuesday we review for the final exam, and I'll have a practice final exam for you. And then on Thursday you take your final exam. Yep. And I'll post the course evaluation soon online, so you'll be able to take that and give me feedback. Okay.
Alrighty, let's do this.
So let's do it. So we were on chapter 8, and we just got to 8.3, Simone.
Yeah. So you said last class period about GBS 250.
Yeah, thank you. So GBS 221, I spoke to administration and Heidi, and they have now put a special permission in for each of you that you can now all self-enroll in GBS 221. So if you just go to your website, wherever that is, you go to your My Maricopa, you can go ahead and sign up for the class right now. So don't do that right now. Maybe during the break or later today when you get home. But yes, you can all now sign up for the course. If you need help doing it, let me know. Okay, so you see these first three questions, 44, 45, 46? You can just cross those out. I was not a huge fan of those. Instead, well, I mean, 47 through 51, I had more poker hands. And we could look at some of those. But maybe it'd be a little bit more interesting to look at these dice games. We don't have to do all of them. In fact, maybe we'll just do a couple of them. All right, so you can cross out 44, 45, 46, and all of page 11. What was page 11 now?
47. 47 through 50.
No, let's look at a couple of those. We'll just do a couple. So for instance, number 48 in poker, if you wanted to build a flush, that means 5 cards of the same suit. So how many ways could you get all 5 cards of the same suit? It would just be, well, first of all, how many cards are there of a particular suit?
13.
Yeah, there's 13. Wait. Yeah, there's 13 cards of a particular suit. So let's consider what our choices are. The first thing we have to choose is a suit. So how many choices of a suit are there? There's 4 choices of a suit. You can either do hearts, diamonds, clubs, or spades. And then once you choose the suit, then you would need to choose 5 cards from the 13 available, and that would be a combination, 13, choose 5. And that's what that would look like. That's the total number of ways that you could get 5 cards of one suit. And notice how this is all about making choices. The first choice is which suit of the 4 will you choose, and then which 5 cards of the 13 of that suit will you choose. And since it's a hand of poker, order doesn't matter because you can rearrange the cards in any order you like. So it's 13C5, not P. And that's it. Now that's the total number of ways you can get a flush. So let's use your calculator and actually compute that. So using your Math PRB NCR button, we have 15, choose 5. Okay, so that's 4 times 1287 is what I got. And then you multiply that times 4, and I got 5,148. So I don't know if that sounds like a lot or a little to you, but there's only 5,148 distinct flushes that you could get out of a game of poker. Okay, however, this question goes beyond that. It says find the probability of this. So now what we want to do is create a fraction. What we want was a flush. The total number of card hands that you could get was 52, choose 5. Because there were 52 total cards to choose from, and you're just choosing 5 of them willy-nilly, just grouping them, not in any order. And so now, again, on your calculator, 52, choose 5. That was that very large number, 2,198,960. So looking at that number, there's 5,148 ways to get a flush, and then there's 2.5 million ways to get a card hand. So then dividing those, 5,148 divided by that number, we get 0.00198, which rounds up to 0.002. So what does that mean? If I move the decimal, you have a 0.2% chance of getting a flush. That's not very good. Right? I mean, 1%. If I told you you had a 1% chance of getting a flush, you're already thinking, gosh, that's only 1 out of 100. That's not very likely. And so 0.2, if you consider it, 0.2 of a percent means 0.2 is really 1/5 of a percent. So that's 1 out of 5 and 1 out of 100. So that's really only 1 in 500 poker hands. If you sat there all night long and played poker 500 times, which sounds super boring to me, but if you sat there and you played poker 500 times, you'd be equally likely as not to get at least 1 flush. So really, during a given evening of playing poker with your friends, should you really expect to get a flush? No. You know, depending on how many times you play. Okay, let's just do one more of those. How about the full house? This full house is pretty popular. So we want to choose 3 cards of one value and 2 cards of another value. So what are the choices we have to make? What's the first choice we have to make? We want to build a full house, and remember what that looks like. That would be like 3 kings and 2 3s. Okay, that's a full house. So the first choice we have to make is the value of the first card. In this case, a king. How many different cards are there? 13. So your first choice is you have to choose one of the 13 cards. And then once you do choose, okay, I'm looking for kings, you want to choose 3 out of the, how many total kings are there? 4. So you'd be looking at 4, choose 3 of the kings. So look at that choice so far. You just chose one particular card, the king, and you chose 3 of the 4 of them. And that now represents your 3 kings. Okay, so what's our next choice? Now that we've used up a king, how many cards are there left to choose from? Only 12. And then from those 12, so we just chose, let's say, a 3. We chose now a particular card. We need to choose 2 more cards, and then we want them to both be a 3. So out of 4 3s that are available, choose 2 of them. Okay, so that right there represents the event of a full house. You chose one particular card to get 3 of them, and then another particular card to get 2 of them, and that's a full house. So now let's compute that. That would be 13 times 4, choose 3, which is 4, times 12 times 4, choose 2. And then we multiply all that together. And it's 3,744. Over the exact same denominator, 259,896. So there are less ways to get a full house than there are to get a flush. Meaning you're more likely to get a flush than you are a full house. And then we divide, 3744 divided by 259,896. And this time I got 0.00144. So that's about, if you move the decimal twice, that's 0.14%. So, considering the previous value was 0.20%, this is 0.14%. So you're a little less likely. Okay, well, I'd say that's good. Just a couple of examples of how to build a card hand. Are there any of the other ones in there that you want to see how to do? Or are we good? Maybe that's enough. All right. The last side is just a couple more overall probability questions. These are some good probability questions. Oh no, I don't have an eraser.
Was I ready to cancel class?
Well, I don't know. Can I get somebody to come up here and lick the board clean? Simone, I think Simone is volunteering. Does that sound very disgusting? Yeah, let's see here.
I have a paper towel. Want that?
Do you really?
I do.
I don't know that a paper towel is actually any good for the board. I'm gonna go look for an eraser.
All right.
It looks good.
If I left for 15 minutes, would you folks be worried? Like, oh no, what happened to Mr. G? Or would you just leave?
We would be worried.
Oh, thanks.
We sent a search party for you.
Thanks. Okay, let's get going here, folks. Last couple questions, some basic probability questions. Now you might say, Mr. G, what's the whole point of all this? Right, I'm a business student, I'm an accounting student. Why, all these games? The idea is setting up your sample space and setting up the event that you want and thinking very carefully. That's a skill for anybody. So let's see, skip number 52 because I think that's pretty easy. 53. 2 6-sided dice are rolled. What's the probability that the sum of the 2 numbers will be 5? So if you roll 2 dice, and hopefully by now you can just imagine that grid of all the dice, what is the probability that the sum of the 2 numbers will be a 5? So how many ways can 2 dice add to make a 5? It could be what?
1 and 4.
Yeah, 1 and 4, or 2 and 3, or 3 and 2, or 4 and 1. So those are all the different ways that you could have 2 dice add up to 5. And it does matter which is which, because this could be a red dice and that could be a green dice. So red 1, green 4 is different from red 4, green 1. Okay, so that's 4 ways out of how many total ways are there to roll 2 dice? 36. And you probably remember 36 because you saw the grid of all the dice. You had 6 across and 6 down. But keep in mind, you could also calculate it by using buckets and saying, how many ways could you roll the first dice? And how many ways could you roll the second dice? And therefore, you have 36 different ways of rolling the dice. Okay, well, that's your probability then. The probability of getting a 5 is exactly 1 9. Okay, I think we've already done number 54 before, so I'll skip that one. Last question, a lottery game contains 25 balls numbered 1 through 25. Do you remember this? Do you remember when they used to do the lottery on TV and they just had balls in a basket?
Oh, yeah.
Do you really remember? Because do they do that anymore?
Not anymore, but they used to do almost like Channel 3 or whatever.
No, but don't they still do it? I mean, that's what Powerball is, right? Isn't that what the big lottery is in Arizona? Powerball?
Digital now.
Yeah, they
Oh, it's
post it-
digital.
They post it online now.
Oh, how interesting. Okay, well, so what is the probability of choosing a ball number 26? Oh.
0.
Yeah, it's just 0. All right, there's no ball number 26 in there, so the probability is 0 ways out of 25.
I'm scared because I probably put a number.
You what? What's that?
I probably would put a number.
Oh.
Still pick 26.
All right, well, getting on reps, folks. So let's put this all in perspective. Chapter 7, we looked at set theory and how to count things.
Wait, Mr. G, are we not doing 56 through 59?
Oh, that's not on my PowerPoint. Let me look. No, let's skip those.
Okay.
Thank you.
Oh, not in front of me. I still.
All right. So then, and then chapter 8, we looked at permutations and combinations. And now chapter 9, we're looking at statistics. Now, to be fair, when you get into GBS 221, the whole course is about statistics.
Oh, fine.
All right, so this what we're about to do is the simplest introduction to statistics. It covers very, very, very basic ideas in statistics. Whereas when you get to GBS 221, and I think his name is Daniel. Well, I don't know his last name.
So we call him Daniel?
No, don't call him Daniel.
Oh. So you said we call you Daniel.
Oh boy, now I'm in trouble.
We got it on
Yeah, we have it on video.
I'm sorry.
His name is Daniel, but his name is Mr. McCroby, I believe. Yeah, Mr. McCroby. There it is, McCroby. Okay, so Mr. McCroby will be your teacher for GBS 221, and it's a lot of statistics.
What if we don't want him to be our teacher?
It's an interesting question.
I think he's the only one that's offering that class.
Correct.
Is that class harder than like this stuff that we just did?
I don't think harder is the right analysis.
Is it harder than matrix?
It's different. Yeah, it's just different. Matrices are just one subject. Statistics is another subject. None of them are really harder than the others.
How would you compare them?
I would say that matrices are pretty far afield of anything you've ever done before, so it felt unfamiliar. Whereas statistics, you talked about mean, median, mode. You've talked about things like that before in your life, so it's a little more familiar, so it might feel easier.
So matrices are harder than matrices.
It's not at all what I said. But I'm trying to respond to this question. All right, let's go ahead, folks. Let's take a look at statistics. Now, first of all, I'd like to introduce you to this idea that you have 2 different types of statistics, okay? One is called descriptive statistics, descriptive. And then another is called inferential. Okay, so descriptive statistics is what we're about to do today. Whereas when you get to GBS 221, you'll do more inferential statistics. So what is descriptive statistics? Is everybody, say around, please, everybody? Descriptive statistics mean you take a bunch of data and you either make bar charts out of it, right? And you just look at it. You're like, yep, there's my data. A lot of people were in this category, not a lot of people were in this category. So you're making basic descriptions, descriptive statistics. You might also then want to calculate something like mean, median, mode. And do y'all remember what those are? What's the mean?
Average.
That's the average. So you add them all up and divide by how many there are. What's the median?
The
The middle.
The middle one. And the mode?
The most common number.
Yeah, the most common. Now this is all still just descriptive statistics. You're just describing your data. These are all measures of central tendency. That's called central tendency. That's trying to say, where's the middle of my data? Another way of saying the middle of the data is saying, what's the most likely thing I will observe in this data? As in, if this is a bunch of people, and one of those people are going to walk through that door, the mean, median, and mode is going to be your best bet of a description of the next person to walk through the door. You know, that's what you'd put your money on, you know? Okay, so those are all central tendency. And then you also have a measurement of variation. How much variation is in that group of people? And one common calculation of variation is range. Are you all familiar with range?
Yes.
What's range?
Between the lowest number and the highest number.
Yeah, the highest number and the lowest number. So like for you all, if you wanted the range of height, I would take the tallest person in here. Who's the tallest person? Anyone taller than me? 6'1"?
I'm 6'1".
Okay, perfect. So Luis is 6'1". Who's the shortest person in here? 5'5"? 5'4"? Anybody want to say?
5'2".
5'2"? Okay, so between 6'1" and 5'2", that's the range of heights. And then if you wanted to be more specific about that, what's the total distance there between 6'1" and 5'2"? I believe that would be a total of is that an 11-inch spread?
Yeah.
Is that really 11 inches from 5'2"? Yeah, because 10 inches will get you to 6 foot, and then 1 more inch to 11 foot. So the range would be 11 inches. Notice that that does not mean that there's anyone in this room who's only 11 inches tall. That just means that that's the biggest gap between the tallest person and the shortest person, right? So that's talking about variation. There's one more computation that talks about variation, and that's called standard deviation. Have you heard of standard deviation? You have?
Yeah.
Well, first of all, standard just sounds like the norm. And deviation means how far do you deviate from the norm. So your deviation is how far you deviate from the average person. So like, let's say, normally we use standard deviation with a bell curve. Have you all seen a bell curve? That's a bell curve. And let's just say that the average height for a human is 5'9". So the average person is 5'9". That's where most people are. And then less and less people are taller than that, and less people are shorter than that. And the height of humans on Earth actually does follow a bell curve. In fact, the height of humans on this campus would follow a bell curve. So when we say standard deviation, it's referring to the deviation from the norm. So like me being 6'1", I would be over here, and I would want to measure how far am I deviating from the norm. That's what the standard deviation measures. How far am I deviating from the tallest point on the bell curve? And so my standard deviation, well, we don't know it yet, but you know, that's what, 3-4 inches? I'm 4 inches taller than average, but there would be an actual computation that we could do to calculate how strange is that. You know, am I freakishly tall or just somewhat tall? And that's what a standard deviation is used for. It's used to describe how much of a deviation is that relative to that population. Okay, so there you go. Those are a bunch of just ideas about descriptive statistics. So what does inferential statistics do? Inferential statistics, you actually start calculating probabilities of some event. So probabilities of something. So for instance, let's just say, well, this is just a silly example, but you're at a movie theater, okay? And you're standing in front of the entrance to one particular movie theater, and out of the door comes a very small child, say a 4-year-old. Now, from that alone, can you infer what movie is going on inside that movie theater?
Scarface.
Yeah, I mean, I don't think so. I mean, if just one 4-year-old child came out of a theater, it could be Jurassic World, it could be Scarface, it could be a cartoon. You don't know, it's just one child. That's not a lot of data to go on, and therefore you cannot infer much. I wouldn't put a large probability on anything at that point. But if you're standing outside a movie theater and 24-year-old kids come out from the movie theater, then could you infer that it's probably Finding Dory or Finding Nemo or something like that? A little more likely, right? So inferential statistics, which is what you're going to do in GPS 221, says look at a little bit of data that you have and what can you say about the population? And that's what they're saying. Okay, so now that you kind of have this idea, inferential statistics is what you'll do with Mr. McRoby, and then descriptive statistics is what we'll talk about today. So far, hey, Josue, have you heard of these ideas, mean, median, mode, range, and standard deviation? Okay, we're good. I mean, that means that this will probably be, pretty normal. Okay, so the first thing that you do with statistics is you draw graphs of your data to get an idea of what your data looks like. We're not going to do a ton of these, but let's do a few. So everybody, let's go ahead and start with number 1. We're going to skip and do every other. So using, oh, you know what? These solutions I posted online, I did the first of every pair of problems. Should I do the second pair of every problem in class? Because then when you go home, you look at the solutions, you can see me doing number 1. Does that make sense? Yeah. That's what we'll do. Okay. So for every pair of problems, I'll do the second one. So it says here, use 6 intervals, starting with the interval 0 to 49. So look what we're going to do here. I'm going to draw this one sideways instead of like a normal bar chart going up. I'm going to go sideways. So we have all this data. Look at all that data. What does it represent? The weight of people on a bus. Is that fine? Yeah, I just totally made it up. And you could have some children on there. You could have some larger people on there. It's just the weight of different people on a bus, right? And so we'd like to know what, generally speaking, is the weight distribution of everyone on the bus. So what you would do is you would chunk the data into groups of the same size. So we're going to do groups of size 50. So we would make a group for 0 to 49, another group of 50 to 99. Go ahead and start drawing. Another group of 100 to 149. And then a group from 150 to 199, and then 200 to 249, and 250 up to 299. Wait, did I skip one? No. Okay, I think that's as high as the data goes. The data does not go above 200. That is 299. It does not go into the 300s. Okay. So now what do? Now, no, do not guess. We go through and you look for numbers in that range, or in that group. So for 0 to 49, I'm going to go through and I'm going to cross out and count any numbers I find from 0 to 49. So that'd be 1, 2. I only found 2. So for now, I'm just going to make a little chicken scratch. 2. That's 2 chicken scratches. That's not a number 11. Okay, now let's look for numbers in the group 50 to 99. So that'd be 1, 2, 3, 4, 5. I counted 5. So I gave myself 5 chicken scratches. And then you just keep on going. Nobody said it was exciting. This is just data. You're looking through the data. You're trying to understand where most of the people are. So now in the low hundreds, that'd be 1, 2, 3, 4, 6. Yes. I got 6 as well. Goody. Okay, and then the upper hundreds, above 150. And notice it's really important that you're actually scratching out the numbers up above. Because that way you know for sure you've counted it if it's scratched out. And as we proceed and you end up with a number that you didn't scratch out, you know you missed one. Now in the low 200s. and then the high 200s. That's it. That's it. It said prepare a frequency distribution with a column for intervals and frequencies. Now, I don't know that I did a column. I think I did a row. But the point is you can prepare the data in a lot of different ways. So this is one way you can prepare your data. And what does this tell you? Where are most of your people? Yeah. In fact, if you turn your head, this is a pretty good normal curve, isn't it? It's a pretty good bell curve. You know, keeping in mind bell curves are what most populations would look like. And then, if you really wanted to, I think it was saying a column for intervals. Yeah, and frequencies. You could have also done this sideways. I mean, this is very exciting. And then you could have had the same thing for your interval of 0 to 49. And then you could have turned it into a bar chart. So you would need some sort of scale. Let's see, the highest it was 6. So 1, 2, 3, 4, 5, 6. Then I could have done, that one's 2 tall. And then my next interval was 5 tall. There we go. And the next one was 6 tall. And 6 tall. And then 3. And then 2. Okay. Now the first thing you're probably thinking is, well, this isn't very hard.
That's how they always start.
Right. And again, this is just showing data to people. Because just imagine if your boss, okay, was like, hey, what's the typical weight of people on a bus? And you walked over to your boss with this list of numbers, you're like, here you go. You threw this list of numbers at your boss. Right? That's the last day of you on that job. Right? Nobody wants to see a list of numbers. So this first part of this lesson is just talking about how do you prepare your data so that it's visually compelling. And I'd say, either way of these is going to be pretty visually compelling. Can you think of a better way to do this? We're just organizing our data. Okay, well, continuing on. That said a frequency distribution. Now, just to be clear, let's make sure that we're using our words correctly. A frequency distribution. So a frequency distribution is purely the number. So if you take a look here, that's frequency distribution. Can you all see this one? They did the tally marks, just like we did, or they just put a number. And so frequency literally just means how many of them were there. So you can see that they have an interval. Here they did the 20 to 30, 30 to 40, and how many people fell into each category, and they either did the chicken scratches, or they just did a number, and that's a frequency distribution, where you literally see the number. So what's the difference between that and a histogram? Histogram. A histogram is a bar graph, right? It's just a fancy name for that. Histogram, etymology. I wonder what histogram. Is that on one? Histogram, and it doesn't even say. Well, that makes, histos, well, anything set upright. I wonder if that literally means that a histogram is a bar chart sticking up. Okay, well, not very exciting. In any case, a histogram just means you make a bar chart. And I tell you what, folks, we already did one of each. Would you agree? We already did a frequency distribution. We already did a histogram. And so that's what number 3 has you set up for. You make a bar chart. Number 4, set up the same way. Would anyone like to do another one of these, or shall we proceed? Let us proceed. Okay, so then number 5 and 6. I did number 5 on my notes, so let's do number 6 together. What is a frequency polygon? I'm going to do number 6 down here. So once again, here we have our height, and they put them in groups. So 63, 64 to 67. How many different numbers are in each group? Like 60 to 63, how many is that? 60, 61, 62, 63. There's 4 numbers in each group. The next one, 64 to 67, that's 64, 65, 66, 67. So they're doing these in chunks of 4. So there's 4 distinct height values in each group. And then they're telling us the total number of employees that went into each category. So as before, you'd make a category for each one. So this is 60 to 63, and 64 to 67, and 68, 71, 72, 75, 76 to 79. And then we need to choose a good scale for our y-axis. What kind of scale should we use? The numbers are anywhere from 24 to 63. So should we go by 10s? 10, 20, 30, 40, 50, 60, 70? Sure, we could go by 10s. That'd be 10, 20, 30, 40, 50, 60, 70. And here's what you're going to do, folks. Just put a dot for each one. So in the 60 to 63 category, there were 26 people, so I'm going to put a dot right there. Pretty close to where 26 would be. 64 to 67, you put a dot at 63. 68 to 71, you put a dot at 49. 72 to 75, you put a dot at 38. And 76 to 79, you put a dot at 28. All right, now right there, you can see how this could look like a bar chart. Right, you just put a bar underneath each of those. But this, they said, create a frequency polygon. And so what they really want is a line graph. These are just definitions. And really, aren't all 3 of these ways a perfectly valid way of presenting data? What do you think, David? Yeah, I mean, these are all fine. We're just trying to show our data so that people can look at the data easily and pick out patterns and say, oh, wow, you got a lot of people between 64 and 67. Not a lot of people between 60 and 63. So this is just a way of making data visually compelling. All right. This eraser was terrible. All right, well, we're done, folks. Not for the whole day.
No.
That was a silly use of language. We're done with those first 6. So when you got really excited.
No.
Okay, now we're going to learn how to use our calculators because our calculators are really helpful. So the next chunk says find the mean of the list of numbers. And it also says round to the nearest 10. Now, how do you calculate a mean?
Mean?
Yeah.
And divided by how many?
Exactly. So folks, everyone do the mean by hand, real quick. That is on your calculator. So you would say, let's add them all. So on your calculator, does everyone have a calculator? I hope. So 6 plus 4 plus 10. I got 47 over how many? 1, 2, 3, 4, 5, 6. Did everyone get 47 out of 6? And then divide. Did everyone get 7.83 repeated? All right. So what does this mean anyway? What does this mean? The mean, 7.83. Were any of our numbers 7.83 repeated?
No.
No. So let's just say that it represented something. Like the average amount of dollars we all have in our wallets. Okay? I'm just putting that all of us have a couple dollars on us as opposed to like a couple hundos. So if that's the average, if those are actually how many dollars each of us have in our pockets right now, do any of us have $7.83? Yes, so none of us do. So when we say that 7.83 is the mean, that doesn't mean that anybody actually had that amount, right? It's just a number, generally speaking, that if you took one of us at random and took all of our money, you could probably expect to get a little over $7. That's what you expect. Okay, well, in any case, now I want to show you how to use your calculator. Ready? On your calculator, you will go to the very aptly described button called STAT, which stands for Statistics. So once you're in there, it says Edit, Calc, and Tests. Under Edit, hit Edit, and you'll have L1, L2, L3. What we like to do is clear out L1. Make sure you have no data at all. So if you push up so that your cursor is on L1, you can hit Clear, Enter, and it will clear out L1. Now, if your L1 is empty, put your cursor back into the L1 column, and we can all now proceed to type in our data. 6, enter, 4, enter, 10, enter, 4, enter, 13, enter, 10, enter. And you should have a nice little list of data. Let me know if you need help getting to that point. Is it working?
Wait, how do I do it on the?
I don't know, Luis.
I have that one.
Yeah, you do. You need to put in your data somewhere.
Sorry, if I do weed, and then now what?
Or I suppose you could start typing in numbers. I've never used that before. Why don't you just type in that list and see what
I did it.
it
It
is?
says incorrect.
Oh, okay, but you watch Adon's calculator. Okay, so folks, that was your stat. Now go back to stat, hit stat. And we've already done, we're done editing. Now hit to the right and go to calc. And you have a lot of options. We're interested in the very first option. So let's explore one variable statistics. This is one variable statistics because there's only one variable. You know, this is the money in our wallet. That's one variable. Hit enter, enter. And now let's all look at what was just presented to you. X bar is 7.833. So what does X bar represent? The mean. So X with bar on top is the mean. Then what do we have? The sigma, that's the sum of X, is 47. What does that mean? What does sigma mean? Because we know what 47 is. 47 was the sum of all the different numbers. So that symbol means the sum of all your data. That's just the sum. And in fact, that symbol right there is the Greek letter sigma, which is the first letter S in the word sum. So that one just means the sum of all your data. What's next? Sum of X squared. Well, there are contexts in which what you'd want to do is take every single one of those numbers, square them, and add them together. So you'd have 36 plus 16 plus 100 plus 16 plus 169 plus 100. Add them all together, that's that. So that's called the sum of squares. Sum of squares. Okay. By the way, do you all see this list that I'm looking at?
Yeah.
Okay. The next one says SX, and that's 3.71. That is the standard deviation. That's what we're going to be really interested in, standard deviation of your sample. Now, that's really interesting. What they're saying is, what did I say? This was the dollars in all of our pockets. But we're just a sample of students here at Gateway. Okay, we're not the whole population of Gateway. If I now went out and looked at the entire population of everybody at Gateway and I told them to tell me how many dollars they had in their pocket, then this list is just a sample of the whole population. And this standard deviation that we're looking at with the S for sample, means that's the standard deviation of just the sample from this room. Whereas the next one says sigma X. Sigma X, and that's 3.387. That's the standard deviation. I will now just write standard deviation of the population. And that would be if these people were all the people. That if I were to say that list of data right there was actually everybody in the whole world that I was interested in, then that would be my population of people. And this standard deviation would be the standard deviation of the whole population, as opposed to the sample standard deviation, which is just the standard deviation of the sample that represents a population. That's a pretty subtle difference. The sample standard deviation is saying that there's actually a much larger group of people I'm interested in, and these are just a few of those people. The population standard deviation says this is the entire population. Okay? Is that all the numbers that were there on your list? What was the last one? N equals 6, because there were 6 pieces of data. Okay, so now everybody knows what we're looking at when you do your one variable statistics. Go ahead and try that again for the next problem. Go ahead and go back to stat, go to edit, and I would again push up, clear enter, and then type in that whole list of data, 30, 60. Once you have that in there, you can hit stat, count, one variable statistics. And I'm going to put up my data that I got, 62.6, 376, 33942. Okay. Did everyone see that data? Or that is, you reproduce that list? Yep. Let's go about that. Oh, okay, yeah, sure. Miss Simone.
I'm there.
Wow. Listen, I'm gonna need some time to just let that let that sit. I mean, man, I feel very happy now in my heart, Simone.
Oh. You didn't give us a jump today.
Oh, well, I can easily correct that. Everyone, unfortunately, I have to leave in 10 minutes. Wait, no, I did have a joke for you. Oh, yes, here it is. This is one of my daughter's favorite jokes right now. What did one snowman say to the other snowman? Smells like carrots. And she's so cute because she'll come up to me at any given day and tell me the joke. She'll say, Dad, what did one snowman say to the other snowman? I'll say, what? She'll say, right, she just says anything, not necessarily carrot. And she knows that snowmen have carrots for noses. She's just being silly. There, Simone, are we good again?
Yeah.
All right, good. All right, button. Can you say what? Yep, now it's that. Yeah, then calc. Go to the right. Yes. Count. There you go, one variable, hit enter. Enter again.
No.
There you go, that's it. Okay, so we've now seen how to use our calculator to do that calculation. Let's move on. Number 10, look at number 10. Now, in number 10, they're telling us not a list of data, but they're telling us that the frequency of each data value. So that in our list of data, there's actually 1 124, there's 5 217s, there's 6 251s, there's 4 310s, and 2 354s. So there's a lot of duplicate data, right? So the number 217 is actually listed 5 times. Now what we'd like to do is find the mean of all that data. So you've got a couple different choices available to you. One is you could actually sit there and start typing all of that data into your calculator, which would be a bummer because you'd have to go to stat, edit, and then clear, and then you'd have to type 124, enter, 217, enter, 217, enter, 217, enter, 217, enter, 217, enter. And after you've typed it 5 times, then move on to 251. 251, enter, 251, enter, 251, enter, 251, enter. Anyway, does anyone want to do that?
No.
No, not really, right? It could be a lot of data. So instead what you do is you do a simple calculation where you set up what will actually be the average or the mean. And you'd say, I have 1 124, I have 5 217s, I have 6 251s, I have 4 310s, and I have 2 354s. That will give me the total. That's me adding up all the data, but in a very fast way. Instead of actually typing it over and over and over, you can just multiply each one by how many there are. And then how many pieces of data do I have? I just add that up. So that's 6, 12, 6, 18 total pieces of data. Do you all agree? So I think that would be a much faster way to get to the mean. instead of typing in all of that terrible data. So now on your calculator, it would just be a matter of typing in your numerator, hitting enter. So that would be 124 plus 5 times 217 plus 6 times 2 plus 4 times 3 plus 2 times 354. And then I got I got 4663 all over 18, which is 259.05 repeating. Did anyone else confirm that answer? Oh, goody. Thanks, Michelle. All right. So that is how you would find the mean of grouped data. Of course, you could still just sit there and type it in. You could just type all those values in. Because notice, I just calculated my mean, but do I know my standard deviation? Like, we will actually be needing this number quite a bit, standard deviation. If I do it by hand like that, my calculator didn't give me the standard deviation. So it could actually be worth it to sit there and type in all 18 numbers. After all, it's only 18 numbers. It's not that much data. Okay, so that's mean. How about median? How do you find the median of a list of numbers? Yeah, you have to put them in order first, right? Are these in order? I'm sorry, let's look at number 12. Are they in order?
No.
No. So we'd have to first put them in order. So I would very carefully cross them out as I go. 2 is the smallest number, then 8, then 11, then 28, then 33.
35, 46.
Hey, 35, 46. Now, at this point, you need to find the middle number. So the middle number, what you can do is start crossing numbers off at the beginning and the end. So like I could go ahead and move in, cross out one number from the right and the left, cross out another number from the left and the right, cross out another number from the left and the right, and I just keep crossing them off until I finally get to the middle number. That's one way you could do it. Now I know that my median is 28. Now one thing that they did not show us how to do right here is what if there is no middle number? Like, look at number 11 real quick and cross out the last 45. Just get rid of it. What is our middle number? There isn't one. 10 and 27 are both the middle number. So what do you do then? What if you get to the middle and there's two numbers? Does anyone know what to do?
Find the mean.
Yep, you find the mean. If you're trying to find the median, but there's two numbers in the middle, not just one, you take the mean of those two numbers. So you'd say, okay, now take the mean of those, 10 plus 27 over 2, which is 37 over 2, which is 18.5. So that's the median. So everyone just make a note of that if there is no exact middle number, and there's two numbers in the middle, then you have to take the mean of those two middle numbers. Oh, this is I've been missing my mouse all day. I just realized that it's right here. Oh, great. All right. All right, so that's median. How about mode? How do you find the mode? What should you do first? Like everyone, let's look at number 14. How do you know which one of those numbers is represented the most? What should we do first? Yeah, always put them in order. That's always a good idea, is put your data in order. So once again, you have to sit there, look for the smallest number, which is 20, and then 24, 24, 24, ooh, 23, 24s, and then 46, and then 49 twice. So what is our mode? At 24. Why? Because it's the most repeated number. Now, to be fair, what if there had been another 49? Then what would my mode have been? Then your population would be bimodal. Bi, like bicycle, two modes. So bimodal is if you had two modes. Suppose you could also have trimodal and come up with all sorts of other names for it, but normally there's just one mode. What if there's no mode at all? What if you list out all the numbers and none of them are repeated more than once? Then you would just say no mode. And in fact, I think number 13 is no mode. Yeah, number 13, there's no mode at all. Well, sorry, how's this chapter so far?
I don't want to say better because I feel like it's going to get worse.
But just right now, how
Just
is it?
right now, it's
Okay, good. And it's because you're familiar with this stuff, right?
Yeah.
Yeah, I almost feel embarrassed. I mean, I think this is very, very simple for a group of mathematicians like yourself. You know, this is easy. You probably did this stuff a long time ago. All right, continuing on. Oh, good. So we have a couple word problems here. The table gives the average monthly high temperature in degrees Fahrenheit for a certain area. Find the mean of the temperatures. So how would you find the mean of all those temperatures? You just add them all up and divide, right? Now, what would be easier? To type all that data into your calculator's stat button and then ask it for the data, or just add them up and divide? Yeah, I mean, just add them up and divide. This problem's not asking you for anything else, so you might as well just add them all together and divide. Same thing goes for number 16, right? Oh, no, number 16 is grouped data. So in number 16, how do you set that up again? You set it up just like that one, where you'd actually have to multiply. Oh, no, I'm sorry. Let me stop talking for a second and actually look at the problem. Grouped data is treated a little differently. Okay, so everyone, you all agree you can just go back and do number 15, right? You just add them up and divide. Look at this one. This is actually different. When they give you grouped data, we're saying that we have 5 numbers between 1 and 5. What number do we actually have in there? We don't know. All we know is that we have 5 numbers somewhere in 1 through 5. And we have 20 numbers between 6 and 10. And we have 25 numbers between 11 and 15. So we don't have complete information right here. We have the frequency distribution that someone prepared for us, but the data itself is not available to us. So how do we go about taking this mean? How do we find this mean? Any ideas? You know, like, let's pretend there's no right or wrong answer. How could you produce a value of a mean that you could feel comfortable with? Like if you wanted to be able to tell somebody what the mean is.
an exact mean.
Well, thank you, Luis. We can't produce the exact mean right now, can we? Because we don't have the original data. So that's off the table. We cannot produce an exact mean. But what mean could we produce that would be pretty good?
Something between the most frequent one.
Hmm? Oh, you mean just choose something in here?
Yeah.
Or maybe just choose a number where it's most frequent? Maybe. That's a possibility, Luis. Anybody have any other thoughts?
The highest and lowest number.
Oh, subtract them?
Mhm.
Or take the average of them?
Yeah.
Oh, okay. Luis is saying just take the biggest number, 30, and the smallest number, 1, and just add those and divide by 2. Maybe that would be it. Anybody have any other ideas?
A number between the 1 and 5 and 6 and 10.
Yeah, you can choose a number in between them. And in fact, that's what the textbook does. The textbook will say, look at the numbers 1 through 5 and take the average of those numbers. So if you looked at the number line of 1, 2, 3, 4, 5, what's the average number between 1 and 5? What's the middle? 3. In fact, if you average 1 and 5, 1 plus 5 is 6, 6 divided by 2 is 3. So what they're going to say is choose the middle number from each of those. That is, take the average. So 6 and 10 is 16 divided by 2 is 8. And 11, 15 is 26 divided by 2 is 13. Take the middle number from each category and use that number as a representative to then do your frequency. To then do your mean. Now, Luis, all of your ideas were fine. They were good ideas. This just happened to be what the textbook did. Okay? So we chose a representative, the middle representative, and in fact, the representative we chose was the mean of those 2 endpoints. Oh, wait, Luis, is that what you're saying? Take the first and the last and add those together and divide by 2? Or are you saying take the first and last number and divide those by 2?
Well, I gave both suggestions.
Oh, yeah, well, there you go. Oh, you did say the suggestion? Oh, I missed it. I didn't hear you say that. Okay, well, there we go. So folks, you would do it just like this one. And you'd say, I have 5 of the 3 data. I have 20 of the 8 data. I have 25 of the 13 data. And so on and so forth. I have 10 of the 18 data points, and 5 of the 23 data points, and 3 of the 28 data points. And I would take all of that and divide it by how many total data we have. So you'd have to sit there and add that up as well. Which is what, 25, 25, 50, 60, 68. And if you do all that, you're going to arrive at a number that is not the exact mean, but is awfully close to the mean. Okay, well, how does everybody feel? That was section 9.1, which I think was called central tendency, measures of central tendency. And so what we just talked about was mean, median, mode, and how to make some sort of a graph of your data before you give it to somebody. Are you all calculating that one? Well, I didn't say anything in particular. I was just giving everyone a chance if they wanted to calculate it. And to compare that with the answer key in the back. I ended up with 879 or 68, which turned out to be 12.93-ish. I don't know how much they rounded.
No, that's what they got.
That is what they got? Well, goody gumdrops. Yep, exactly. All right. Okay, so the next section is called measures of variation. And you can see they give 3 ideas: range, variance, and standard deviation. And in all 3 of those, you might want to circle the word variation and make a little note. We're talking about spread. How spread out is your data? You know, is your data really tightly clustered around a central value, or is your data really spread out? So for instance, if you looked at an entire school, like let's consider height. If you looked at an entire school and you looked at the height of everybody, your data is going to be really spread out because you're just looking at a random group of people. And so you're going to have lots of tall people, lots of short people, lots of middle-heighted people. Whereas if you were not just looking at a school in general, but instead you were just looking at to be a stereotypical basketball team, then I'm thinking that for the most part, your athletes are going to have more of a grouped cluster of people that are all fairly tall and maybe even really close in height to each other. Is that a gross generalization, or is that okay? Is that okay? I mean, maybe you disagree. You're like, no, Mr. G, really basketball players can be short and tall. But does someone have a better example of who's a population of people that they're all going to be fairly tall and the same height? Some sort of athletes? Maybe basketball? Yep, this seems like a fine choice. So the key thing is here that you can either have data that is really, really spread out, or you can have data that is really, really dense. And this is meaningful in terms of whether or not you know someone is an oddball. Okay, now oddball, that sounds mean. I'm not calling any of you oddballs. I would call Simone an oddball, but she's not here. But you know, when is something strange and out of the ordinary, and when is it perfectly ordinary? So like, for instance, if I was said that somewhere at this school there is a 4-foot person, I don't think any of us should be too shocked because we're a huge school. There's a lot of different people that go here with a lot of ages going all the way down to high school, what, 9th graders here? So if we were looking at this data and I said there's a 4-foot person in there, you wouldn't be shocked. But if I was looking at the basketball team and I said, hey, there's a 4-foot person in there, I think that you would be shocked. You'd be really surprised. So spread, talking about measures of variation, range, variance, and standard deviation, knowing how tightly compact your data is or how spread out your data is going to give you a measure of surprise. You know, would you be surprised if you had this data? Would you not be surprised if you had this data? Okay. So, taking a look there at the first one, find the range for the set of numbers. What's the formula for range? Somebody already said it. Lata, what was range? We don't actually have to add up anything.
Just the highest and the lowest?
Yeah, it's just the highest minus the lowest. So we can just look at that data and say, well, 16 looks to be the highest, 2 looks to be the lowest, and so we just subtract high minus low, and that gives us 16 minus 2, which is 14. So 14 is the difference between the highest and the lowest person. So again, looking at my data that's really, really spread out, we have somebody who's really tall, 6'5", somebody who's really short, 4 foot. So our range would be approximately 2.5 feet. Whereas on the basketball team, if the tallest person was, say, 6'4", and then the shortest person was, say, 6'1", then our range is simply going to be 3 inches. So when you're looking at data that's really, really compact, you'd expect a smaller range. When you're looking at data that's really, really spread out, you're looking at a range that is a much larger number. That tells you something about the population. Okay, well, range is a pretty basic idea. You can't do much with range. So, I would like to introduce you to the bell curve. Everyone, you need to take out a sheet of lined paper. Let's take out a sheet of lined paper, and you're going to draw a bell curve over and over again. And then some more, and then some more. You're going to draw a bell curve so many times. Now, are you all familiar with seeing this graph? What do you call this graph? A graph. Very good, it's a graph. I think there's 2 names that you normally call it. One is called the bell curve. Do you know why it's called a bell curve?
It looks like a bell.
Yeah, it looks like a bell, right? And then the other name for it is called the normal distribution. Yeah, I know, I had them both up there. So this is called the normal distribution, as in the normal distribution of data. So if you just take, now this is what's really strange here, this word normal, what they mean is a normal population. In a normal population, you have a huge diversity of genetics, you have a huge diversity of children, you have a huge diversity of parents, and you tend to see every potential trait that you could possibly see. Right? So you're going to have short people, tall people. You'll have tall people with brown eyes and short people with brown eyes. You'll see every possible combination in a population that is normally distributed. Whereas, like if you just went to, say, one particular town in Switzerland, and everyone was blonde, 5.5 feet tall, with blue eyes, then you'd say, well, this particular town, everybody kind of looks the same. But when we talk about normal distribution, you're talking about seeing a huge wide range of characteristics. Furthermore, you do expect, when you look at any particular trait, and I'll talk about height a lot, height is a good trait, that if you take any group of, say, 100 people, and you plot their height on a graph like this, you tend to have a big cluster of people around the average or the mean, and then you've got a few people that are taller and a few people that are shorter. And that's basically what you'd expect. Let me contrast that real quick. If you went to a movie theater and it was showing a kids movie like Finding Nemo, I'm so out of it. What's a more popular cartoon movie? Anyone? Are we all out of it?
Kids must review.
What's a popular cartoon movie?
They're for kids.
The Incredibles.
Oh, it's Incredibles? Okay. So if I went to a movie theater and I plotted the age or height of everyone in that movie theater, you might see something that looks like this. Right? Where this is the age of, 9-year-olds, and then this is the age of, say, 30-year-olds. So you could get a population distribution that doesn't look normal at all. Because the data I happen to be looking at is movie theater, where you have a whole bunch of parents taking their kids to go see a movie. And whereas when you go see The Incredibles, you're going to have parents with their kids, but probably not too many 18 to 20-year-olds, because they're too cool for that. And they're seeing a different movie, right? So this would not be a normal distribution. This would be a bimodal distribution. Okay, so then just to be fair, I just want to make sure we all know, not every population is normal. Some populations are not normal. But we're going to be talking about normal distributions because they have this nice characteristic shape. So here's what I want you to see. And everybody, I'm going to use some data that you can all verify for yourselves. I want you to draw this with me. So make a bell curve. And it doesn't have to be perfect, just make it a bell curve. And what we're going to do is the average male height. Or better yet, let's do the average female height, and let's just verify, because this is the kind of thing we can check. Mean female height, US. Here it is. The average height for adult woman varies around the world. In the US, the average woman is a little under 5'4". Oh wait, where's I want mean standard deviation. There we go. No women are on average a bit shorter or less variable in height with a mean height of 65 and a standard deviation of 3.5. Well, let's all just pretend and say that the mean is 65 inches and the standard deviation is 3. Can we do that? We're going to say the mean height of a female is 65 inches and the standard deviation is 3. So let's draw this out together real quick. So everyone right smack dab in the middle, let's put 65 inches. And again, this is the female height. And what is 65 inches? That's 5'5". Okay? So that's the mean. And again, where do you get mean from? You type in a bunch of data into your calculator, you hit one variable statistics, and then that's the mean. That's X bar. Right, X bar. So standard deviation. Standard deviation was one of the other values that your calculator gave you. And we're saying in this case that the mean is 65 and the sample standard deviation, what was the symbol for it? S with an X? Was 3 inches. Now what does that mean? What we're going to do is off to the right, we're going to mark off tick marks. And every time we go one tick mark, we're saying we're going 1 standard deviation to the right, which means I add on 3 inches and now I'm at 68 inches. So that's 1 standard deviation to the right. I'll even put a little 1 right there. And then go 2 standard deviations to the right. We're counting standard deviations. If I go 2 standard deviations to the right, that means I will have now added 3 inches twice and now I'm at 71 inches. And now I'll go 3 standard deviations to the right. And so add 3, add 3, add 3, I'd be at 74 inches. So a woman who is 74 inches tall is technically 3 standard deviations above the mean. A woman who's 71 inches tall is 2 standard deviations above the mean. And a woman who's 68 inches tall is 1 standard deviation above the mean. We could get even more fine-tuned and talk about a woman who is 72 inches tall. How many standard deviations above the mean is she?
2.5.
Yeah, 2 and a bit. Well, we don't know exactly what the fraction is there, but 2 and a bit. She's 2 and a bit standard deviations above the mean. Now we can go to the left. Put tick marks to represent standard deviations to the left. So now we're going to subtract 3. So 65 minus 3 is 62. She is -1 standard deviation to the left. And then go another standard deviation, -2 standard deviations to the left. She would be 59 inches tall. Right? We're subtracting by 3, which is our standard deviation. And then subtract 3 again. A woman who's -3 standard deviations to the left, that would be 56 inches tall. Now what about a woman who is exactly 65 inches tall? How many standard deviations above the mean is she? None. Right? So I want you to notice what I've done here in my drawing, which you have also done on your drawing, because you're all drawing this, right? So the numbers on top are just keeping track of how many standard deviations you are above or below the mean. So you can very easily just look at those numbers and say, hey, I'm 2 standard deviations above the mean, 3 standard deviations above the mean. Or you could actually look at the real data itself and say, I'm 74 inches, the average is 65 inches. So there's our standard deviation. And that's how you count. So these two numbers go hand in hand. Mean and standard deviations above the mean. One more thing to mention. Let's fill this in now. Put a vertical line going 1 standard deviation above the mean and -1 standard deviation below the mean. I want you to memorize this number. How much of the population of females will fall between a height of 62 and 68 inches? Meaning, how many women are exactly are within 1 standard deviation of the norm? And the answer is, for any normal distribution, always 68%. So 68% of any normal data will fall 1 standard deviation from the mean. So it doesn't matter if you're talking about height or inches or what. So long as you're looking at a normal distribution of data, 68% of all of your observations will fall within 1 standard deviation of the mean. Okay? What about 2 standard deviations of the mean? What percent of women will fall between 71 inches and 59 inches? In other words, what percent of women will be 2 standard deviations from the mean? So now if we look at all the women in this whole chunk, okay, the whole area here, that answer is 95%. 95% of all data will fall within 2 standard deviations of the mean. So that's it so far. And then finally, 3 standard deviations. How much data will fall within 3 standard deviations of the mean? The answer is 99.7. Now we have to be specific there, 99.7. If you just round it up, that'd be 100%. That'd be wrong. But 99, it's more than 99, you know. It's 99.7. That's pretty much almost all of it. So how much of your data falls within 3 standard deviations of the mean? 99.7% of your data. Together, these 3 numbers are called the 68, 95, 99.7 rule. And what that means is that if you're looking at normal data, that is populations that are normally distributed with a single bell curve, that 68% of your population falls within 1 standard deviation of the mean, 95% of your population falls within 2 standard deviations of your mean, and 99.7% of your population falls within 3 standard deviations of the mean. So just as a real quick question then, what percent of your population is more than 3 standard deviations away from the mean? If 99.7% of all people are within 3 standard deviations of the mean, how many people are more than 3 standard deviations from the mean? 0.3%. Now keep in mind, the 0.3%, so 0.3% are more than 3 standard deviations from the mean. But keep in mind, there's 2 tails, right? You could either have people who are super tall or people who are super short. So that 0.3% you have to cut in half and say 0.15% are taller than 3 standard deviations. and 0.15% are shorter than 3 standard deviations. All right, so that's the standard deviation. I'm sorry, that's the normal distribution. And that's how you read the normal distribution. So let's take a look back at this picture that I had up here. U, which they don't necessarily use in this chapter, so we don't have to worry about it, but the Greek letter mu is typically the letter that you use for mean. Mu, mean, mu. And then sigma is the typical letter for standard deviation. So you can see here that what they're saying is that mu is the mean. That's 1 standard deviation to the right, 2 standard deviations to the right, and 3 standard deviations to the right. Whereas mu, going backwards, that's 1 standard deviation to the left, 2 standard deviations to the left, and 3 standard deviations to the left. And so the main questions we'll be asking are, what % of people, like this would be a question you could ask, what % of people fall within 1 and 2 standard deviations above the norm? Right? Like if you're just talking about like, who are these people right here? These people are average. These people right here, a little above average. These people right here, you know, significantly above average. And who are these people over here? Like super duper above average. Right? So we could ask questions about what % of people are here, what % of people are here, and so on. That will be the questions that we're going to ask. Okay, you're probably all like, Mr. G, great, your phone went off, let's take a break. Well, let's just look at this one real quick. See, this is the actual height of women who are in the ages of 30 to 39. I don't know what year this was, but you can see it's fairly normal. You know, it looks like a normal curve. And then this is the difference between men and women. In both cases, they both have a standard deviation. No, I'm sorry. The adult male had a standard deviation of 4 inches, and then the adult female had a standard deviation of 3.5 inches. So you can tell the female height is a little more clustered. It's a little skinnier, whereas the male graph was a little wider. So male height is a little more spread out, and female height, they tend to be closer clustered together. Okay, well that is a good time to take a break. The time is 3:26. Let's be back at 3:36. I'm going to go find some new markers.
You said what? I'm about to say, you should let me call her and tell her it's fine. So what did she say? Like, she said, oh, you know what? Let's tell her it's fine. What did she say?
She's like, whatever, we're just gonna go with it.
Oh, okay.
And then the other president, she's the dress is fine. Now she's worried about her family.
Oh.
I guess they got snagged or something. I'm like, oh, that's not my responsibility. That's yours. She said, eat.
I got it. Shut up. I swear that that's the best one I've ever heard. Well, make up your own business. Good God, job. Good God. Did you text me?
No.
It must have been the other guy. Text me about some accounting homework. I'm like, what the fuck is this?
Probably what's his name?
I don't know. I didn't even say his
Schmidt?
number. Ishmael.
Whatever. Or
Ish something.
I don't know. Ish or
Yeah.
he texted.
I guess so. I'm like, damn, didn't I say save my shit?
He doesn't want to date with you.
Nigga, do not play that. The minute I saw it, it
He's trying to hit.
didn't stop.
Did you reply?
Um,
Who it is?
oh, so I was gonna text back who this, but I didn't send it. Damn, that's what. But whatever. I'm like, oh, I didn't even do that. I did not say save. I didn't even save y'all. Let me see if she sent it to me.
What did you do the homework that you have sent me?
Where's that one? What homework?
Or the GPS?
Lewis,
I did my homework. Yeah, I did it.
you don't show up to account.
Stop.
It's a hard class to
Was it?
Yeah.
Are you gonna be
so
so confused?
confused.
21?
I don't know. I have to go. I have to take it.
What's
Because
our
that would
homework?
be like my 9th class.
Yeah, we have.
Well, you're
to
gonna be
take it.
done with this one though. You're
I
gonna
What's our
know,
homework?
but I'm fucking tired. Because
What?
after I'm
What
done
is our-
with this one, I start another one, and I still have a lab.
What's our homework for?
So, my
accounting?
schedule's packed.
Last time I'm gonna
Excel.
finish this one, but then I'm gonna sign up for 221. But then I started
Do what
CIS.
to it now?
Yeah,
CIS
I start
blows.
another
What?
GPS.
We have to do
You
it all.
can't listen to 3 different. I need you
But
to.
I graduate this.
What is the homework for accounting? Excel.
My only last class
Yeah,
is
the
gonna
one
be
that we
the
started in class, we have to
accounting
finish all that, the
But I'm
horizontal
gonna
and
take
vertical.
that Glendale.
I thought we. What
Right.
more?
Well, because it's only
Was
offered
class
there
up here?
during summer.
Oh, okay.
Or was
It's
that?
gonna be my
Oh,
own.
we have my accounting lab homework too.
Yeah, no, I don't understand what she's talking about in 2:30.
Yeah, Mrs. Biggs blows.
Like, she does it so relatable. Like, I understand what she's talking about in
You're
there.
gonna air
But once it comes to the
her
test, I'm like, what the fuck? You didn't teach us none
I'm
of this
surprised she's married. She doesn't deserve it.
Damn.
Honestly,
I hate her.
yes. Like that bitch trying to get the zero, literally a zero in the class. How? How do you get a zero in the class? Let me stop. Because I'm about to spaz out. No, not in accounting. I'm talking about in the last class I took for her. And like literally every assignment I like submitted, she put a zero for it. Yeah. So no, I don't like that.
Man, you must have fucked up.
And that in that class, I was like so like I was literally actually a student. I was quiet. I didn't talk to nobody.
That's probably what was wrong.
Oh, I should have talked.
Yeah.
Yes.
Oh, yeah, that happened to me, but I kept sending her email. I did the assignment, and then she got tired of me emailing her. She started putting in my scores.
Oh, yeah. That's another thing. I'm up there like, yo, bitch, I'm gonna take this shit. And she was like, I don't talk about it in class, and then she never talked about it. And now I'm emailing her, and she's not responding. I'm like, I'm gonna fuck you. Don't play with me. So close to being done too.
You should email her again.
I did.
Well, you weren't there today.
So fucking complain about a zero and not be there.
B, how can I complain about what?
A zero and not be there.
That was last.
That's how
week
life
before
works.
That shit was.
class.
That
What-
was gonna
what'd you
happen
get on
this
the
semester.
test?
But I was there every day.
Would you get on the test?
What test?
The one we
Yeah,
took
she
last
did
week.
it.
Shut up. The one I took for I got a C. Six, almost a 70, I think. 69 or something. I don't know. So I'm trying to bust my
Ooh. I got a 44 on it,
good job, but you didn't get a zero.
but I got 100% on both the extra credits.
Did she already put them in?
She hasn't updated anything.
She does it to the very last day of class.
Yeah, she'll update everything the day before our final, and then I'll know.
That's when you know you're failing and shit.
Yeah.
Yes.
That's kind of dumb.
She
It
offered more
is.
extra credit last semester.
Yeah.
That's how I passed the class.
Yeah,
I
so
don't think we got.
we got a shit ton of extra credit. I had like a 90,
Like, just going to the
and I
learning
went
center
into the
to
final
Lorena,
field
we got
and got a
extra
C, and I was like, peace.
I went in there and I got like 15 extra credit points, which helped me pass the class.
She won't
I was
give
never
you
going, I
a lot
would've
of
never
extra
passed the
credit. It's because I need it, like absolutely need extra credit in that class, and so she probably won't get all of that this semester.
She gave up a lot last night. There was like extra credit every week she was giving us. She was like, do this, it's extra credit, do this.
I know, like before the test, we had like so many practice tests, and they were all extra credit.
She realized how many kids were in our class last semester, and then now this semester's only like 10.
And yet they still keep dropping. Like Frankie's not there no more.
Oh yeah,
I know.
I forgot about
And
her.
she's like, Frankie, what is that for? I'm like, just like, no, just Frankie. She's like, oh.
Jackson West Jackson dropped it. That's
I
it.
haven't seen him.
He plays baseball.
His grandfather was on the campus.
I didn't know so much about him.
I went to high school.
You went to
I work for his
what's
grandfather.
what's that high school called?
Arcadia.
Arcadia, yeah. That's crazy. Y'all principal left y'all school just to go to our school.
To Central, Mr. Vieira. You
Yeah.
guys gave him a pay raise.
Oh.
Because Phoenix Union, yeah, they do.
Yeah. Starting is like almost is like 60. Just to be a teacher there. So there's kids. What?
Sounds familiar.
No, Phoenix is like the best district to go work in, but you gotta deal with all the students.
Mhm.
So you gotta go teach. Like one of our teachers left to go teach at Trevor Brown because they offered him 75. So he was like, peace. Yeah, we had 3 like principals leave to go to Central. Mr. Vieira left, and then Mr. Mooney, and then somebody else left with him. And then you guys had Obama come to your school.
Yes. Dope ass. Wait. See what?
Oh, I see how it
He's gonna be like, higher now.
I forgot about that, but Obama.
Yeah, Obama went to Central. What did he even go to Central for?
Who went to Trevor?
You didn't, you don't want
Someone went to Trevor.
Really, one of the most ghetto schools.
I was like,
Yeah, I'm gonna go to Arizona to go to Trevor Brown in Central.
I was actually there.
What did he even go for?
Who?
Obama.
That's so crazy. I don't know. I was just hyped to see Obama. I bet you if I look on my Snapchat, there's probably two there. I was hyped.
one of your stories throwback.
Yeah. I met Obama. Guys,
All right, folks,
we made it.
let's keep going.
Okay. I was hyped. I'm not good on camera.
Wait, what year did you
We
graduate?
have 1 more hour to learn about standard deviation.
You know what year you graduated high school?
You guys ready? Adon?
I'm guessing.
Simo? All right. So, find the standard deviation for the set of numbers. Over the years, I've often required students to be able to do this calculation by hand. But the fact is our calculator does it for us. And to do it by hand is very lengthy and time consuming, whereas we have this technology available to us. So I say we use it. Find the standard deviation for the set of numbers. You will go ahead and go into Stat and Edit and clear out whatever list you have and put in your new numbers, 9, 16, 7. And then you hit your stat, your calc, 1 variable statistics, and we're going to write it all down and draw a nice little picture. So I see that my X bar is 10.5 repeating. Oh, that marker looks so much better. And my standard deviation, my sample standard deviation is 4.45. Well, I mean, it's 4.447. Ooh. So depending on how you want to round it, how much accuracy is really going to matter to you in your particular problem. All right, 4.4. Okay.
Would you want us to round it or actually write out 3 decimal places?
Well, I think the program is probably going to want 3 or 4 decimal places. So 4472 there. So that's your standard deviation. So now let's look at what that actually means and let's say something meaningful. So whatever this data is, would anyone like to pretend what this data represents? It could represent dollars in our pockets. It could represent Let's just go with that. Let's just go with that, dollars in our pockets. So what we're gonna do in terms of making our diagram, we're gonna make it really nice and user-friendly. We're gonna say the average is 10.5, and we're going to say the standard deviation is 4.5. Because that way it's easier to add as we go to the right and left. So here's what we're gonna do. Everybody make your standard deviation, or I'm sorry, make your bell curve. And you put your average right in the middle, 10.5. So the average amount of money that any of us have in our pockets is $10.50. Now, we'd like to use the normal distribution to make statistical or probabilistic statements about people and the money they have in their pocket. So let's go one standard deviation to the right and left. So if you go one standard deviation to the right and one standard deviation to the left, you're either going to add 4.5 to 15 or subtract 4.5, which would be what, 6? All right, but don't worry, everybody. Buzzer got curly fries to share with all of us.
Nice.
Good man, Buzzer. All right, so now what can we say? Using our 68, 95, 99 rule, what we can say is that 95% of us, okay, that's impressive, 95% of us are between $6 and $15. Oh, I'm sorry, that's not the rule. 68%. I'm so sorry. Well, I said that wrong. The rule is 68, 95, 99.7. So now consider the number 68%, by the way. 68% is awfully close to 66.66666%, which is 2/3. Right? So with this rule, we're actually saying 2/3. Right? Roughly speaking, 2/3, 2 out of 3 people are going to have between $6 and $15. That's what we just got out of this data statement. What can we say next? Count up one more and count down one more. Go up one more standard deviation, so now up 2 standard deviations. Now we're going to be at 19.5, and down 4.5, that'd be what, 1.5? So now down 2 standard deviations. Now what we can say is that 95% of us are between $1.50 and 19.5. And already, that's pretty much everybody, right? If I calculate 95% of 10 people that are in this room, 95% of 10 is 9.5 people. And 9.5 people would round up to 10 people, which is 10 out of 10 people. So when we say 95%, we're already saying almost everybody. Like nearly everybody. Okay, now let's complete the rule though. To finish the 68, 95, 99.7 rule, now go a 3rd standard deviation above and a 3rd standard deviation below. So add 4.5 one more time, so that'd be 24 up here, and then subtract 4.5 one more time. That would put us at -3. Now you'll notice here that doesn't make so much sense. Can anyone have -3 in their pocket? Well, maybe. Adon owes me $3. So yeah, Adon could have -3 in his pocket. Oh, what we're saying now is that 99.7% of people in this room, according to that data, 99% of people will be between, I'm going to say, 0 and $24. And in fact, that's basically true. If you look at the data, every single piece of data up there is between 0 and 24. So it almost just becomes like vacuously true. Like, well, yeah. Basically, everyone's between 0 and 24, but yeah, that's true. I mean, all the data falls into that range. All right? So that's a normal distribution. That's how it works. And what we do is we count standard deviations. So again, this person, it's $19.5, but it's 2 standard deviations above the mean. And this person is $6, but it's 1 standard deviation below the mean. So we create this new language that says I'm 2 standard deviations above the mean, I'm 1 standard deviation below the mean, because then it doesn't even matter what you're talking about. You can take away the fact that you're talking about height, you can be talking about money, you can be talking about weight, you can talk about age, and saying that I am 2 standard deviations above the mean still says something. Anybody would still say, oh, 2 standard deviations above the mean? That's pretty significant. You know, you're pretty far away from the average. You know, not a lot of people are 2 standard deviations away from the mean. Okay, I tell you what, the next 2 problems, all of you can just type that into your calculator and do it. So let's move on. You can finish those for your own homework. Now, you can all go ahead and just scratch out 22 and 23. I don't feel the need to make you suffer through doing standard deviation of group data. So let's proceed now to Chebyshev's theorem. Number 24, Chebyshev. Oh, Chebyshev. That's right, you all know about Chebyshev. Gosh, I hope I'm pronouncing his name correctly.
You're probably not.
Hey, I've taken multiple statistics classes where my teachers have said Chebyshev. Those nouns, Chebyshev.
Chibu. The sweetest song in the world.
I don't hear any volume at all.
It's Russian.
You have volume at the bottom.
Where?
Left.
Left.
Right.
Right, it's 100. Well, that was very, very anticlimactic. How about I use my own phone? Not that it matters, but you know, I suppose we should try to be saying person's name correctly. But that begs the question, will the person in the video pronounce it correctly?
The world may never know.
Oh my gosh. Pronouns. Chebyshev. Oh, here we go.
Pronouncenames.com.
Yeah, that sounds.
Chebyshev. Yeah, I mean, this guy sounds a little sad. Chebyshev. Well, I'm going to continue saying Chebyshev.
Do we have the correct pronunciation?
They don't even know. All right. So Chebyshev's theorem tells us something similar to what the normal distribution tells us. It's just another statistic that you can use. And so here's what it says. Chebyshev's theorem. So good old Chevy. Chebyshev. Theorem states that I want to say it exactly right for you folks. I don't want to just ballpark it. Where did my notes go? I wrote it down. You all see it. And of course, I didn't write it down. Okay. What the heck? I really thought that it said it right there in the notes. And it doesn't. All right. Yeah, there we go. Yeah, it's a lower bound. So, Chebyshev's theorem. The fraction of data K, yeah, that is K standard deviations from the mean is at least 1 minus 1 over K squared. And so we'll apply this a couple times to see what it means. So the fraction of the data that is K standard deviations from the mean is at least this much. So we're saying that we have at least this many people K standard deviations from the mean. So let's try this first problem, and we'll apply that. So in a certain distribution of numbers, the mean is 50. So everybody go ahead and draw your bell curve. You're going to draw a bell curve for every single problem going forward. So just get in the habit of just making a quick little bell curve. The mean is 50, and the standard deviation is 6. So I'm going to start counting to the right. 1, 2, 3, 4. Left, 1, 2, 3, 4. That's 4 standard deviations right and left. And I'll go ahead and start counting up now by 6. So 56, 62, 68, 74. And then to the left, subtract by 6. 44, 38, 32, 46. All right. So there's definitely quite a bit of repetitive adding and repetitive subtracting that you'll be doing. And the question they're asking is, use Chebyshev's theorem to tell the probability that a number lies in the indicated interval. So what percent of numbers will fall between 26 and 74? Oh my gosh, that first number was a 26. There. So they're saying between 26 and 74. Well, I did exactly from 26 up to 74. And how many standard deviations is that? 1, 2, 3, 4 to the right. 1, 2, 3, 4 to the left. So we're really saying within k equals 4 standard deviations. So what percent of data will fall within 4 standard deviations of the mean? And so we go ahead and compute this number. You would say 1 minus 1 over k squared, which is 1 minus 1 over 4 squared, which is 1 minus 1 over 16. And how do you do 1 minus 1 16th? How do you rewrite the 1?
16 or 16.
Yeah, 16 16ths. So now we have 16 16ths minus 1 16th. And the answer is 15 16ths. And you'd want to put the word at least. So at least 15 16ths of the data is going to fall between 4 standard deviations of the mean. And this simultaneously answers the question, what is the probability that you choose a number between 26 and 74? The probability is 15 16ths. So we're saying two things there. That in this data, whatever this data is, 15 16ths of the data will fall between 26 and 74. And therefore, if you close your eyes and just grab somebody at random, there's a 15 out of a 16 chance that you grab somebody between 26 and 74. And again, this only works if you're looking at normal data, normal distribution data. So, oh my gosh, I wrote it on the next page. For any set of data, the fraction of the is at least that. There we go. I knew I wrote it down somewhere. Sure. Okay, so let's keep the same drawing, and let's look at what they're saying now. Now they're asking, erase, what is the probability that you choose somebody who's less than 26 or more than 74? So that's number 25. So what would that mean? Now, I'm looking at my standard, I'm looking at my bell curve again, but I want to know the probability of people over here or over here. So we already knew, what was the percentage of people in here? This was 15 16ths, right?
Yeah.
So there's a 15 16th probability. So what's the probability that you're out here? 1 16th. But we have to keep in mind, this one is at least 15 16ths. So now if we're computing these tails, that'll be at most 1 16th. Or if you don't want to use the phrase at most, you could also say not more than. Not more than. So not more than 1 out of 16 people will be in those two tails of the distribution. By the way, we call these the tails. This is a tail, this is a tail. And we call it the tails of the normal distribution. I don't know of any animal that has two tails, but we refer to this as the tails of the distribution. Okay, how about the next one, between 35 and 65? Everybody, do we have a 35 and 65 on our numbers? No. 35 falls between 32 and 38, doesn't it? And what's the other one? 65 falls between 62 and 68. Anyone want to take a guess at where 35 is? How many standard deviations to the left would it be? It's left 1, 2. It is 2.5. And then where would 65 be? It's right 1, 2, and 2.5. The fact is, you can go ahead and write down that it's k equals 2.5. How would you prove that to yourself? How would you prove that 35 and 65 are both halfway between those? Well, you'd have to check.
Guess.
No, don't just guess. So you have 32, 33, 34, 35, 36, 37, 38. And we want to know where is 35? So that's 37, 36, 35, 34, 33. Okay, now is everyone convinced that 35 is halfway through? So in other words, then if that's 1, 2, if this was 2 standard deviations to the left and this was 3 standard deviations to the left, then this is 2.5 standard deviations to the left. So you kind of have to, do a little work, figure out what your k value is. Now everybody, we can go ahead and do our computation again. 1 minus 1 over 2.5 squared. And, you might just want to do it all in decimals. And then at the very end, you can hit the math frac button and get your fractions back. So 1 minus 1 divided by 2.5 squared is 0.84. And as a math frac, that's 21/25. So there's a 21 out of 25 probability that you randomly choose a number between 35 and 65. This is Chebyshev's theorem. Now, the whole point of Chebyshev's theorem is that it's just an easy formula. 1 minus k squared is an easy formula. It's also not incredibly accurate. It would be better to actually just use the actual normal distribution table, which we're going to learn how to do in a second here, and actually just look it up. But Chebyshev's theorem it's just a quick, easy rule that anybody could do off the top of their head without needing to carry around one of these with them. So by the way, did everyone get one of these? Okay. So we're going to learn how to use that in a second here. But Chebyshev's theorem is just a simple way. All right. Well, let's keep on going. Number 27 is a simple word problem. I think we could probably skip it. It just says, well, let's just look at it real quick. The real skill that we need to build is reading word problems and building models. So it says the manager of an electrical supply store measured the diameters of the rolls of wire in the inventory. The diameters of the rolls in meters are listed below. Find the standard deviation. Okay, well this is not very exciting. You just type those numbers into your calculator and you get the standard deviation. Okay, so I'll just assume that you all are going to do that. Let's keep going. It looks like the next few problems all just ask you to find the standard deviation. So if you all don't mind, I'm just going to leave those to you. You just type it in your calculator, find the standard deviation, and let's move on to the interesting section, section 9.3, the normal distribution. All right. Oh, this is going to be so much fun, folks. This is going to blow your mind. You're going to be so, I don't even know how you lived before today. So first of all, have any of you used this normal distribution table that you see here? Have any of you? Maybe yes, maybe no. Everyone start on the page where it says, everyone start on the page where it says table 2, and then the first value is negative 3.4. Oh, actually, I suppose the first page is technically the 0 mark. Yeah. Does anyone need one? Everybody has one? Actually, we'll start with the positive z values. What's that? So start on the page where up at the top it says z and then 0. So first of all, everyone, let's just learn how to read this table, shall we? So let's begin. Now notice they give us a drawing on the other side, and the drawing they give us is that they are going to tell us the amount of area to the left of the z value that you compute. There. So there, does everyone see that little picture at the top of the page where there's a z? I should probably put my z more like there, because that's where they had it. There. So does everyone see that picture up at the top? So first of all, what is z? Z is the number of standard deviations you are from the mean. So everyone, first of all, let's all just agree that z is the number of standard deviations you are to the right or left. Okay? So keeping in mind that that's what z is. Z is the number of standard deviations you are to the right or left. We've already been practicing that. Let's go ahead and look up some values. Okay? So let's find z equals 0. what we'd be asking then is how much area is shaded to the left of z equals 0? How much of the bell curve is shaded? Now you should all be able to answer this question off the top of your head because the bell curve is symmetric, 0 is in the middle. How much of the bell curve is shaded? 50%. And sure enough, if you look up the very first line in the table, it says z. Right below it, what you do, the first decimal of accuracy is along the left-hand side. So that's 0.0. And then if you read along the top, that gives you the second decimal of accuracy. Okay, so if you wanted the z value of 0.00, you start on the top line of 0.0 and you go to the right just once underneath the second decimal of accuracy, 0.00, and there you can see the number 0.5, meaning that half of the graph is shaded to the left. Okay? What if, okay, let's change this a little bit. What if you wanted to go to z equals 0.5? So how much area is shaded to the left of half a standard deviation? So everybody go down and look up 0.5 on the left. And the second decimal of accuracy is going to be 0.00. So we're looking at 0.500. And what percent, or that is, what fraction of the area is shaded? Yeah, 0.6915. So in other words, 69%, well, yeah, 0.6915 of the area is shaded to the left of z equals 0.5. Okay. What about z equals 1? If we wanted to know how much of the area is shaded to the left of z equals 1, that is the whole darn thing, everywhere to the left of 1 standard deviation to the right of 0, how much area is that that's shaded? So everyone finds z equals 1, and then just go to the right once so that you're looking at 1.00. And what's the amount? So Dia, what's the amount for z equals 1.00? I might not have explained myself very well up here, so I need to make sure everybody can read it. So we're looking at z equals 1.00, because that's 0.00. So it'd be 0.8413. Does everyone see 0.8413?
Yeah.
Okay. So that's the total amount of shaded area to the left of what? Now, folks, let's be clear about what 0.8413 means real quick. This means two things, which I need to say. One is that that's 84%, 84.13% of the bell curve is shaded in. Okay, so you just move the decimal twice. And you're saying that to the left of 1 standard deviation, 84% of the bell curve is shaded in. But the other way to think of it is that we say that the total amount of area under the bell curve, the total amount of area is 1. So what we're saying here with the 0.8413 is that we've shaded in 0.8413 of that total area, which the total area is 1. So every number that we look up is always going to be a number less than 1. And that number is going to represent a probability or the percent of the area that's shaded. So everybody, let's try looking up a weird one. How about z equals 2.25? Z equals 2.25. Everyone, what amount of area is shaded in to the left of 2.25? So down the left-hand column, go to 2.2. And then across the top, go over to 0.05. And then go down and find the number that goes with 2.25. What number did you get, Simon? Bata, what did you get? So you go down the left-hand column to 2.2, and then go to the right until you get to 0.05, and then find that number. And what did you say, Simone? Yeah, 0.9878. Bata, did you find that?
Yes.
Okay. David, did you find it? Yeah. Okay. And Sarai, you found it? Okay, let's try it. So you want to look up the value z. Oh. Z equals 0, and then we're going to go down to 2.2, and then we want 2.25, so you come across the top, that's 0.05. So that's 2.25. Okay, Luis, did you find it?
Yep.
Adam?
Yep.
Michelle?
Yes.
Josue? Okay. All right, so folks, now let's go ahead and go back to the first problem. So we'll start reading the problems they gave us. It says, find the percent of the area under the normal curve between the mean and the given number of standard deviations from the mean. So everybody, draw a bell curve, just a nice little quick fella. Make a 0, and then go over here to the right and put 3.01. That means we are 3.01 standard deviations from the mean, to the right of the mean, And I'd like to know how much area is to the left of that. That's the only thing the table can tell you, is all the area to the left. Okay, that's all the table knows, is all the area to the left. So everybody look up 3.01, and what did you get?
0.9987.
Very good, 0.9987. So what that means is that 99.87% of the bell curve is shaded. So the probability of falling in that region is 0.9987. Furthermore, then, how much of the bell curve is to the right of 3.01? What's the probability of landing in that tail to the right of 3.01? If this is the area to the left of 3.01, how do you find that area to the right? You subtract. You do 1 minus 0.9987. Everyone do that on your calculator. What do you get? If you do 1 minus 0.9987, would you get 0.0013? Everyone do it on your calculator. Because here's the thing. This table only tells you area to the left. So if you want area to the right, you have to subtract from 1. Okay? So in this particular problem, what we're saying is that the probability that you are more than 3.01 standard deviations from the mean, above the mean, that probability is only 0.0013. So very, very unlikely. Let's try another one.
So what's the answer for that one then?
What's the answer? What's the question? It says find the percent of the area under a normal curve between the mean, between the mean and the given number of standard deviations. Thank you, Josue. So what they're really asking is how much area is here between 301 and 0. Thank you, Josue. So how much area is that? What do we do, folks? We know that all the area to the left of 3.01 is 0.9987. But we're only interested in this area. So what do we have to subtract out? We have to subtract out this left-hand side. And how much area is in the whole left-hand side?
50?
Yeah, 50% or 0.5. So if you just want this darker blue region here, between 0 and 3.01, you do 0.9987 minus this 50% over here. So now let's do that. So that'd be 0.9987 minus 0.5. And so that the final answer would be 0.4987. Thank you, Josue. I totally forgot about that. Okay, so folks, do you see that there's two different things for subtraction that you could do? They're giving you the total area to the left of a number. So if you want the area to the right of the number, you do 1 minus that. But if you just want the area between the standard deviation and 0, you take that number and subtract 0.5. So let's write this in a more concrete way. This whole thing over here is the 0.9987. So the whole left-hand side is 0.9987. If you just want the little tail to the right, then that's 1 minus 0.9987, right? And that was the 0.003. But if you just want this chunk right there, between 0 and 3.01, then that means that you would have to do 0.9987 minus 0.5. And that would give you just that little chunk right there. Okay, I think my diagram is still a little small to demonstrate all that. Maybe I should have it nice and big. So here's 0, here's 3.01, and the number that we could look up on the table was everything to the left, which was 0.9987. So all the area to the left of 3.01 is the 0.9987. So if you just want this area, so this little tail right here, then that's going to be 1 minus 0.9987, which is the 0.0013. Whereas if you just want this area, you would need to do 0.9987 minus the 0.5, which is 0.4987. Whereas how much is the whole left-hand tail, or the whole left-hand side? Always 0.5. Okay. So does everyone see where we get all these numbers from? If you're landing in the left-hand side, it's 0.5%, or half, 50%. If you want to be in this little tail, it's 0.0013. If you want to be in this chunk right here, it's 0.4987. Okay. Thank you, Josue, for reminding me about that. Let's try another one. Let's look at what they're asking. At number 32, and draw a picture with me now. They're asking how much area is between 0 and 1.64. That's the question they're asking. How much area is between 0 and 1.64? So the only thing the table will tell you is how much total area to the left. So what is the total area to the left? That's what you look up on the table. So everybody look up 1.6 on the left-hand column. Go to the right until you hit 0.04, and what number do you get?
0.9495.
Yeah, 0.9495. So the total area to the left is 0.9495. So then we only want this area though, so we subtract out the 0.5 that's in the left-hand side. And so we would get 0.9495 minus 0.5, which is 0.4495. So that's the total amount of area that's just right there. Does that work? How does everyone feel about that? Once again, our table is only ever going to tell you the total amount of area to the left of the number you're looking at. So then you have to do some subtracting to get the actual area that you want. Let's try it again with 0.35. You got your bell curve, you're at 0, you're interested in 0.35, and you want that area between 0 and 0.35. And notice what we're asking. We're saying, what percent of people are between the average and 0.35 standard deviations above the average? We're looking at people who are slightly above average of whatever you're talking about, you know, height, weight, whatever. So everybody look up 0.35. So you'd have to look up 0.3 along the left and then go to the right until you hit 0.05. And what number did you get?
0.6368.
Yeah, 0.6368. So that represents all of the area to the left, 0.6368. So you notice how I'm drawing that. I'm drawing myself a nice arrow that points all the way to the left. So all the area going to the left is 0.6368. But the whole left-hand side of the graph is 0.5. So what will we do? And we'll just subtract 0.6368 minus the 0.5, 0.6368 minus the 0.5. And that tells us that it's 0.1368. That's the amount of area in that chunk that we're interested in. David, how are you feeling? Bata? Well, the very next one, number 34, is technically a repeat. We already did 3.01 on the z-score, didn't we? So let's skip that one. Or I can just make up something new. Let's just make up something new. Let's cross out 3.01 and do 2.5. So what percent of all people will be between 0, that is the mean, and 2.5 standard deviations to the right? That is, how many people are between average and 2.5 standard deviations to the right? So we would look up 2.5 on the data table, telling us how much area is there to the left. And I got 0.9938. But I'm only actually interested in the amount of area between 0 and 2.5. So if that's all the area, 0.9938, I subtract out the left-hand side of the distribution, which is 0.5. And so that little chunk of area right there would be 0.9938 minus 0.5, which is 0.4938. So in other words, 49.38% of the people are between 0 and 2.5 standard deviations above the norm, or above the mean. Questions on that part of the process right there? Because we're about to switch and do something a little different. What about that?
2.5.
Yeah, I just rewrote a new number in there, 2.5. Because we already did 3.0 a couple problems ago. How's that? Done?
Good process.
All right. So let's look at this next one, folks. Now they're saying, what's the total percent of people that are going to appear between 0 and negative 2.41? So we're looking for these people right here. How much area is there right there? What's the probability of landing in that chunk right there? Well, when we look up 2.41, first of all, you have to turn your paper over now because that's negative 2.41. So if you look up negative 2.41, what do you get?
0.2082.
Yeah, 0.008. So let's all keep in mind, that means the amount of area going to the left of that is 0.008. Well, that's not the area we're interested in. That's the only area we can look up in the table. So that little tail right there is 0.008. So then how much area is there in the shaded region that we're interested in? Keeping in mind that the entire left-hand side is 50% or 0.5. So we know that the entire left-hand side is 0.5. The tail is 0.008. So what are we interested in?
Gotta be 20.
Just give minus 0.08.
Yeah, it'd just be 0.5 minus 0.008, which would be 0.492?
Yeah.
Yeah. So 0.492, that means 49.2% of the people will fall between the average and 2.41 standard deviations to the left of average. Serona, was that okay?
Yeah.
Okay, now here comes a really exciting one, folks. You might want to draw your picture even bigger. We want to know what percent of people would be between, I'm going to put a 0 in. I always put a 0 in just so you can see it. Between negative 0.36 and negative 1.1. So what percent of the people, and go ahead and draw it and shade it, what percent of the people fall right there? So how do we do this?
Find both and subtract them.
Yeah, absolutely. You find both and then subtract. So keep in mind, let's just find each of these now. I'm going to find all the area to the left of negative 0.36. So I'm going to draw that here. The area to the left of negative 0.36. So I got to find negative 0.3 and then go over to 0.36. And I got 0.3594. So that's 0.3594. So the total amount of area to the left of negative 0.36 is 0.3594. And then I'll find the total amount of area to the left of negative 1.1. So I go to negative 1.1, that's 1.10, so it's the first entry. The total amount of area to the left there is 0.1357. So now what? We know the total amount of area to the left of negative 0.36 is 0.35. The total amount of area to the left of negative 1.1 is 0.1357. So how much area is there left in between them? And what do we do with those two numbers?
Subtract.
We just subtract them. And that will tell us the total amount of area in between those two numbers. So 0.3594 minus 0.1357. And I got, I don't know about you, 0.2237. Is that what anyone else got? What questions would you like to ask, folks? Ooh, really nice drawings, by the way. Lovely drawings. What are your notes?
Taking over my.
I would write some of these down, brother. Please.
No plan in drawings.
Woo!
I almost got that. I saw that hand.
I appreciate that you're participating and watching, but I would really be writing these things down because this, if you don't write it down, it's you get home and you're like, what did we do? Okay, I can barely see the last one. What does the last one say? Is that 0.7?
Yeah.
And 1.98? Okay, so everyone try it. Everyone try that. You want to find the total amount of area between 0.7 and 1.98. And remind yourself what we're even talking about. We want to find the total amount of area. I'm going to do mine big up here. So I'm doing the one currently that we're on. I always put down 0, so I know that 0.5 to the left, 0.5 to the right. And I want to know the area between 0.7 standard deviations to the right and 1.98 standard deviations to the right. So I'm looking at that slice of society, those people right there that are 0.7 standard deviations above the norm to 1.98 standard deviations above the norm. And all I can look up in my table is total area to the left. So I look up 0.7, and total area to the left of that is 0.7580. Then I look up 1.98. 1.98. And the total area to the left of that is 0.9761. So then, how much area is left in between the two? Don Luis, aren't you just so happy that you're actually doing this one?
Yeah, I love it.
You're like, yeah, this does feel better. So did everyone get 0.9761 minus 0.7580? And you got an answer of 0.2181? Okay, so the 3 different ways to interpret that result. The total area under the bell curve is 1. Total area under the bell curve is 1. So if you wanted to calculate a probability, remember, probability is 1 out of total, and what you want is the 0.281 out of the total, which is 1, and therefore it's just 0.2181. That's your probability. If you move it to the right 2 places, that tells you 21.8%. 21.8% of your data falls in right there. Okay. I guess that was just really 2 ways to interpret the data. What we just did was a whole lot of practice of just looking up numbers from your table. Now on the test, you won't be allowed to use the table. You have to memorize it.
I'll take that.
I'm kidding. So, there's our normal curve. Yeah. Find a z-score.
That's it for today.
Yeah, no. That's not good today. I don't get it. That's... Oh, okay. Well, this is good practice. So now they're going to ask us to go backwards. Find out what the z-score would be to find a given amount of area. So everybody, they're saying, what is the z-score? And remember, z-score is number of standard deviations. So take a look here. Take a bell curve, and they're saying, where would I have to draw the line such that only 4% of the area is to the left of z? So keeping in mind, if I drew my line in the middle, 50% of the area would be to the left of z. So where should I put my line? If I only want 4% of the area to be to the left. Like there? Would that be a good spot for my z-score? That only 4% of the area is left? Does that look like a reasonable guess? So we're looking for a z-score that's left of 0, which means we're looking for a negative number. So let's go find, on your table, a negative number where the answer is the decimal 0.04. Okay, we want to go find a z-score, which we know is going to be way off to the left. And the answer in the table is going to be 0.04. So can anybody find in the table the decimal 0.04? It won't be exact, but you can find 0.04. Where did you find it? Within the table itself.
Negative 1.7.
Yeah, negative 1.7 what?
0.05.
Yeah. Everyone look at negative 1.7 and then go to the column 0.05. So the answer is negative 1.75. The z-score would be negative 1.75. If you only wanted 4% of the area to be to the left of your z, you would choose the z value, negative 1.75. Now, is that completely accurate? Would it actually be 1.75 exactly? No. It would be between 1.75 and 1.76. So the real answer is between negative 1.75 and negative 1.76. But that's pretty close. So did everyone see that in the table? Did you find the 0.04 about that?
Yes.
Did you find it? There was a 0.04 right there. So from that, we're able to look up negative 1.75. Sadia, did you see it? Yeah, that's it, exactly. David, did you find it?
Yeah.
And Adon, did you see it?
Yeah.
You did? Are you lying to me?
No, I never lied to you.
Luis, did you find it? Okay. See my time. Josue, did you find it? And Michelle, you found it? Okay, super. Okay, well, let's try another one. Ooh, 4% of the area is to the right of z. Everyone draw that. We only want 4% of the area to be to the right of z. But remember, our table only looks up area to the left. So if it's 0.04 to the right, what's the total amount of area to the left? If it's 0.04 to the right of z, how much area is to the left of z? 0.96. So we want to now go look up the decimal 0.96. Keep in mind our z value is far to the right of, so we're looking at a z value that's probably like 2 or 3. So everyone flip back over to the positive z side and scroll through all those decimals until you find 0.96.
1.8.
I did not get that answer. I got 1.76.
1.8.
Now go up to 1.7. The very first time you see the decimal 0.96 is between 1.75 and 1.76.
Yeah, 1.75 is closer.
Yeah, okay, yeah, that's fine. 1.75 is closer. But it's between 1.75 and 1.76. Do you see about that? You're looking for, yeah, there is a 0.96, but there's one up here. Right there. No, right there. That's the first one. There, that's the first one. Okay, did you find it, Sabi? That's it, you? Okay. And David, you found it? Yeah. Michelle? Elsewhere? Luis? Yeah. Okay. Okay, so therefore, the z-score that we'd be interested in would be 1.75. Yeah, 1.75. Between 1.75 and 1.76. You know, if you wanted to be a show-off, you could be like 1.753. But you'd just be making up the 3, right? Okay, now here's a really good question. We want 20.1% of the total area to be to the right of z. Now see, this is just good, careful, slow thinking. So first of all, 20.1%, move the decimal back to the left. We're really looking for 0.201. And they're saying they want 0.201 to the right of z. So z is over here, and we want 0.201 to be to the right of z. But our table only tells us area to the left of z. So how much area is to the left of z? How would you find that on your calculator? Yeah, 1 minus 0.201, which would be 0.799. Is that what we're all looking for? Actually do 1 minus 0.201 on your calculator and see what you get.
Yep.
Okay, so we're looking for 0.79 to the left of z. So in your table again. In you go. And you're looking for 0.799. So 0.799. I found 0.799. Where did I find it?
0.8.
Yeah, 0.8 what?
4.
Yeah, 0.84. So 0.84 would be the z-score. What does that mean? It means 0.84 standard deviations to the right of 0 will give you a point on the curve where you have 0.201 area to the right and 0.799 area to the left. All right. We can skip number 41. You can just cross it out. Let's go ahead and try some real problems. This is just us learning how to use the table. We now get to actually do real questions of industry, answering real questions about a manufacturer of parts. Don, how you doing? Good. How's the team doing? All right. I would highly recommend that you write this next one down.
I've been writing them all down.
Oh, good. All right. So go ahead and read through the introduction to this problem set. It says, a company installs 5,000 light bulbs. So just imagine that was all the light bulbs in this building. Okay, so we just have this whole main building, 5,000 light bulbs. Each light bulb has an average lifespan of 500 hours. So everybody, let's begin our drawing. Each light bulb has an average life of 500 hours. So 500 goes right in the middle. What is our bell curve talking about? Hours of bulb life. So how long a bulb lasts. We could even label the axis, that's hours. The standard deviation is 100 hours. So if you start making tick marks to the right and tick marks to the left, then one standard deviation to the left is 600 hours, two standard deviations to the right is 700 hours. A standard deviation to the left is 400 hours, and a standard deviation to the left is 300 hours. So the standard deviation amount is 100 hours. And the distribution is a normal curve. Find the approximate number of bulbs that can be expected to last the specified period of time. So the first two questions are gimmies. The first question is, how many bulbs will last at least 500 hours? So how many bulbs will be over here? Half. So actually do half, that's 0.5, right? The amount of area is 0.5. Half of the 5,000 light bulbs, and the answer is 2,500 bulbs. Because keep in mind, we're actually talking about light bulbs, so the answer should be light bulbs. Next question, what % of light bulbs will last less than 500 hours? Also half, because that's, that's what mean means. The mean of 500 means that half will last longer, half will be shorter. That's actually what the mean means, is that half of everything will last longer than it, and half of everything will last less than it. So that's also 2,500 bulbs. Okay, now here comes some fun ones. Between 500 and 675 hours. So on our distribution, we've got 500, which is the middle, and then 675, which is here. And we want to know how many bulbs, how many, mind you, not a percentage, but an actual number of bulbs will last. It's a really interesting question. This is powerful. So the first thing we need to do is not talk about bulbs, but talk about standard deviations. So remember, the middle is 0 standard deviations. So how many standard deviations to the right is 675? 1 point something. Yeah, very good. You know it's 1 point something because 675 would be about here. And so you know it's 1 point something. Well, there's a formula that actually tells you how to calculate a z-score. It's very simple. It makes a lot of sense. And it's z equals your number minus the mean divided by the standard deviation. So x is your number. So that's going to be 675. minus the mean, mu, the Greek letter mu is mean, which is 500, divided by the standard deviation, that's sigma. The Greek letter sigma for standard deviation is 100. And that gives us 675 minus 500 is 175 divided by 100, which is 1.75. Would you all believe that that sounds reasonable?
Yep.
1.75? That's the number of standard deviations you are above the mean. So you might just want to remind yourself then, for this formula, maybe you're going to write it nice and big somewhere, the z-score is x minus mu over sigma, where x is your data point, mu is the mean, mu for mean, and sigma is standard deviation. And that little formula will just go ahead and calculate for you how many standard deviations you are above the mean. Okay, so now we have to actually do the actual problem. Now that we know that we're between 1.75 and 0, what do we look up on our table? The total amount of area to the left of 1.75. The total amount of area to the left of 1.75 is 0.9599. But I'm only interested in this area to the right of middle. So what do I do to my 0.9599? Subtract out the 0.5. That's all the way to the left. So I would have 0.9599 minus 0.5, which gives us 0.4599. Now we're not done yet. That's just a probability. That's the probability of all bulbs that are in that shaded region. That's the percent of all bulbs that are in that region. What we want to do is actually tell somebody a specific number of light bulbs. So what do we do now with our number, 0.4599? Multiply it times the 5,000 bulbs that we installed. Because we're saying that 0.4599 of the 5,000 bulbs will last between 500 and 675 hours. So 0.4599 times 5,000. And the answer I got is 2299.5, which rounds up to, the 5 rounds up to 9, the 9 rounds up to 9, 2,300. 2,300 bulbs. Now we just did something really interesting. We just used statistics to play the mind of God. That's what we just did, and that's what inferential statistics means. This is what you're going to do in GBS 221. You're going to predict the future. That's what inferential statistics allows you to do. Descriptive statistics just describes the data you have right now. Inferential statistics predicts the future. And by using all of this data, we just predicted that 2,300 of our light bulbs are only going to last between 500 and 675 hours. Which means at the end of 675 hours, how many light bulbs will we have needed to replace? 2,300 bulbs. That's the prediction. That's the prediction ability. Okay, let's try another one. Number 45. I don't really have a lot of space right here, so I'm going to do it right here. So we have our bell curve. 500 is in the middle, and we want to know how many bulbs are going to last between 290 and 500 hours. So we've got 290 and 500. That's the shaded region to the left there. And I know that 500 represents 0 standard deviations. So where's 290? Would anyone like to just ballpark it? 290 would be how many standard deviations to the left? 1, 2, 2 and a bit, 2.1, 2.2. It's 290 is real close to 300. So yeah, probably 2.1. That's a fairly good guess. Let's actually do our formula. Z equals x minus mu over sigma. Notice that we're going to get a negative number because if we do 290 minus 500 all over 100, then that's negative 210 over 100, which is negative 2.1. And that's what we'd expect. We'd expect a negative z value to the left. So we're actually looking at the z value, negative 2.1. And we want the area between negative 2.1 and 0 standard deviations to the left of the mean. Those are great drawings. Looking good. Good 2 set A. Nice. All right, so what do we do then? What's the only thing we can look up in our table? The total amount of area to the left of negative 2.1. That's the only thing the table tells us. So let's look up negative 2.1. And that tells us that the total amount of area to the left is 0.0179. That's how much area is to the left of negative 2.1. But we want the total amount of area here. So how do we do that? Yeah, subtract. We know all the areas to the left of middle is 0.5. So we subtract 0.5 minus 0.0179. And that gives me 0.4821. 0.4821. That is the probability of a light bulb being in that area between 290 and 500 hours. Note, that's still not the answer. The answer they want is a total number of bulbs. So how do we calculate a total number of bulbs? Multiply. Yeah, multiply that times 5,000. And so the total number of bulbs is 2,410 bulbs. And keep in mind that I'm not trying to be, what's it called? Sacrilegious when I say the mind of God. Maybe I can just say we're trying to be omniscient. That's what we're doing. We're being omniscient. We're saying that 2,410 bulbs are in fact going to fail between 290 and 500 hours. That's what we're saying here. And that's what makes that inferential statistics. I changed my phone alarm. That tells me that we still have 1 hour left. Okay. Now, just to see, oh good, I just have 2 more slides worth of questions. And so let me just see here. I think what I'm going to do then is focus our attention on 46, 47, and 48. And I'm going to hope, yep, yeah, these 3 will be our last. And I just will make sure that none of the other problems are on your test. So let's try 3 more problems with standard deviation and the normal distribution. Here we go. A machine produces bolts with an average diameter of 0.3 inches. So everybody, draw your normal bell curve. And the average is 0.30, or just 0.3, but I'm going to put 0.30. Right? That's the average. The average is the mean. It goes in the middle. The standard deviation is 0.01. So as you make tick marks, going to the right and left is going 0.01. So that'd be 0.31, 0.32, or going to the left, 0.29, 0.28. Those represent your standard deviations. What is the probability that a bolt will have a diameter greater than 0.32 inches? So we're looking for this area over here. What's the probability that the area falls over there? So what was our z-score? This was 0, 1, and 2. And that's -1, -2. So we want to find this area to the right. Our table won't tell us the area to the right. So we need to find the area to the left and then subtract. So how much area is to the left of z equals 2?
0.9772.
It's what?
0.9772.
Okay, so there's 0.9772 area to the left of z equals 2. So then you subtract it from 1. And so the total probability of being in that tail would be what? Is it 0.0228? Anybody who used their calculator? All right, thanks, Michelle. So what that means then is they say, what is the probability? Well, the probability is 0.0228, or if you wrote it as a percentage, move the decimal twice, and that'd be 2.3%. So 2.3% of all of their bolts should have a diameter of 0.32 or bigger. That's what they would expect.
They just have it as 2% in the answer keys.
Yeah, they didn't do a very good job, did they, Josue? We have a little more accuracy, don't we?
I don't know, we might be wrong.
No, we're not wrong. It says round to the nearest whole percent.
Oh.
So they just rounded. Okay, let's try again. The mean clotting time of blood is 7.35 seconds. So the mean clotting time is 7.35. With a standard deviation of 0.35. All right, so as we go up and as we go down, we have to add 0.35 and subtract 0.35. So that would be 7.7, and then 8.05, and then 8.4. Or if I subtract, that'd be 7, and then that'd be 6.65, and then again, that'd be 6.3. Okay, so that's just adding 0.35 over and over again, and that's subtracting 0.35 over and over again. You can feel free to use your calculator. Key thing here they're saying is, what's the probability that the blood clotting time will be less than 7 seconds? So here's 7 seconds, and we want all the area to the left. So what standard deviation is that? That was 0 in the middle, and that was -1. So that was -1 standard deviations to the left. And so that's what we're asking. We're saying for a z value of -1, what's the total area to the left? And this problem was pretty convenient because that's what the table's going to tell us, is the total amount of area to the left. So if you just look up in your table, z equals -1, the total amount of area there is 0.1587. Which, if you move the decimal twice, that's 15.87, which I would round to 15.9%, but the book would round, or your answer key would round to 16%. Is that right, Josue?
Probably.
Well, it's okay, Josue. You don't. I just thought maybe you already did. Number 47.
But it is 16.
Yeah. Okay. Okay. One more, folks. Now, by the way, perhaps you're looking at me counting up and down all these numbers, and you're like, "Oh, gee, Mr. J, I don't want to do all that." Remember, you don't have to. You can just use your z formula. So the z formula is x minus mu over sigma, and in this case, your data was 7 seconds minus the mean, which is 7.35, divided by the standard deviation, which is 0.35, and that gives you -0.35 over 0.35, which is the same, -1. So I got my z equals -1 by just looking at my numbers, but you can also calculate the z by looking at your z formula. Okay, we're gonna do one more. Don, that's amazing that you're gonna write these notes down on your paper in your backpack. Yeah, let's just set up one more problem, folks. If you have to go, I understand, but let's do one more. The average size of the fish in a lake is 11.4. So as always, you put 11.4 in the middle. And it says with a standard deviation of 3.2. So if you don't want to write out all the 3.2s, you don't have to. You can just make a note that sigma is 3.2, mu is 11.4. And it says find the probability of catching a fish longer than 17 inches. Well, 17 is way over here, and they're looking for the probability longer than. So they're looking for the area to the right. So the first thing we need to do is find our z-score, the number of standard deviations. So z is actually x minus mu over sigma, which is 17 minus 11.4 over 3.2, which you'd have to use your calculator to get that z-score. So 17 minus 11.4 divided by 3.2. Did anyone else get a z-score of 1.75?
Yep.
Goody. So now we look up z equals 1.75, but you have to keep in mind that they're going to tell you the amount of area to the left. So when we look up z equals 1.75, yeah, it's 0.9599. So that's how much area is to the left. So then you have to subtract from 1 to get the area to the right, which is 0.0401, which if you move the decimal twice, that's 4.01%. And if you round like the book does, that's just 4%. So what did we just say? The probability of catching a fish longer than 17 inches is only 4%. Thank you very much, folks. I realized there were a couple problems left, but you can just not worry about those. Although it's a very easy problem, they're good problems to do. Bye, David. Bye, Luis. What's right?
Yep.
How did the day treat you?
It was good to me today.
Did all of this stuff make some sense?
Yeah, this chapter is pretty good.
Oh, good. I said let's see, there's me. Yeah, it was Slade, Cheryl, Sarai, Sabina, David, Don, Papa. No Diego. Wasn't he here? He left?
Yeah, he was here.
Luis, Simone. Simone left. I wonder why Diego left. He didn't say anything. I wonder why Simone left. She didn't say anything. Just sneaking out notes. What's wait, did Simone tell you when she left? Why she left?
No.
She used to say,
He just left.
Michelle, she didn't tell you either?
No.
Oh, well. What can you do? She didn't tell me either. Simone, you hear that? You didn't tell anybody.
So Mr. G, tomorrow, I just got a